Hey guys, back for another lesson. This is the one right after Halloween. Hope you guys had a good, safe Halloween. Kind of continuing where we left off. Got some pretty good problems to do in this lesson. But of course, we need jokes. Why are giraffes so slow to apologize? It takes them a long time to swallow their pride. This one's better. How do you catch a squirrel? You climb up a tree and you act like a nut. Not too bad. Okay, today we are going to continue on in what we were doing. And remember, we were talking about, if you're following, ways to solve for the energy or the delta H in reactions. And the first way was stoichiometry, and I did that in the last lesson. And then we got into the second way, which is calorimetry, and that's what we're going to get into today. And really what's behind calorimetry is this thing Q-SMAT, or what I call SMAT plus CAT. We're going to get in and do some pretty good problems today. Hopefully they will make sense. But here we go, into kind of picking back up where we were. This is where we were, and we talked just briefly about this. So on this slide, a calorimeter, I always remember this means a calorimeter. It's a device that measures delta H of a reaction by simulating the surroundings. And there's two kinds of calorimeters. One, and to be honest with you, the problems we're going to do, it doesn't matter if it's a bomb calorimeter or a coffee cup calorimeter. Technically, I'll explain the differences between them, but really the problems we do are going to be done the same way. And what you do is, like, say you're trying to figure out the calorie of a Pop-Tart or a potato chip, you just put it down there in the bomb calorimeter where the little wires are, and you burn them, and you just measure the change in temperature of the water is what you do. But in a constant volume calorimeter, you cannot have any change in volume. If you remember, then work was equal to negative P times delta V. So in a constant volume calorimeter, work cannot be done. But in a constant pressure calorimeter, technically you can. But like I said, in the problems we do, we're really both calorimeters. We're going to do Q-SMAT, and then today I want to do one that's a SMAT plus CAT problem. And so again, now you can see what we did in first year chem, and we're extending it. But delta H of combustion reactions use constant volume. Most others use constant pressure. But again, doesn't matter the kind of calorimeter. We're going to do the same kind of problem. You can kind of skip around in the notes here a little bit. I'm going to go on to this page just to explain, since we just talked about calorimeters, the difference between the two calorimeters. And if you notice in this reaction, in a constant volume, a bomb calorimeter, I think they call it a bomb calorimeter because the pressure can build up. But notice the value for delta E. And then if you look at a constant pressure calorimeter, notice the delta E is a little bit bigger. Well, that's because in a constant pressure calorimeter, technically work can be done. Now, again, in the problems we're going to do, they're going to be done all the same. Oops. Okay, so a calorimeter is only capable of measuring Q or delta H. It cannot measure the work done when expansion takes place. So calorimeter, we're really either kind of calorimeter, we're not going to be able to measure the work done because there's not going to be any change in volume. When an exothermic reaction occurs in a calorimeter, the calorimeter temporarily absorbs all the heat given off. So the Q of the system equals the Q of the surroundings, which means really what we can say is this. And this is kind of at the crux of what we're going to kind of going back to the beginning of the chapter. But what we're going to say then is that if you remember that in a calorimeter, and again, in the problems we're going to do, technically, I'm probably making this confusing because I'm a little confused. But what we said in an earlier lesson, we said delta E, the internal energy, was equal to Q plus W. What I'm saying is in the problems we're going to be doing with a calorimeter, of course, I was just saying under a coffee cup calorimeter, they can measure volume changes. But in the problems we've done, I've never seen that. So what that really means is we can just take out W. These calorimeters are not going to measure W. So delta E is equal to Q, which is really equal to delta H. So what we're going to do here is we're going to do, to find Q, we're going to do SMAT do a problem like that. And units will be important here because we will do this in kilojoules per mole. And then I'm going to add, oops, what I call CAT. So we're going to do SMAT plus CAT in solving for Q for the energy given off. And then they'll see if they want us to do this in kilojoules per mole or not. So all that being said, technically delta E is equal to Q plus W, but in these calorimetry problems, because there's no change in volume, doesn't depend on what kind of calorimeter. And you'll see the information that the problems give us, they don't talk about a change in volume. If they did, then we would factor that in, but they don't. So delta E equals Q, delta E equals Q, which equals delta H, if that makes sense. Okay, so now here, let me do a couple of example problems. And to me, it's plug and chug, but there's a lot of numbers and there's a lot, you got to look at it. So, okay, so we've done this slide. I'm actually going to go backwards. So here's an example of a problem, a calorimetry problem. So if I read this out, okay, so again, I think in these AP chemistry problems, there's always so much information. It's, to me, writing things out is always beneficial. Okay, so you can read this. Okay, now I'm going to work this problem on the board. Okay, so it says in a coffee cup calorimeter, so we've got NaOH, and it says that it's 100 mils, and it's 1 molar. And then we're mixing it with HCl, which I think again is 100 mils, and it's 1 molar. Both solutions were initially at temperature 24.6. So the temperature was initially 24.6. And after the reaction, the final temperature, so temperature final is 31.3. And don't have to convert to Kelvin here. You can do this in Celsius or Kelvin. You could. And it says, assuming the solutions have a density of 1, so the density is 1 gram per mil. And the specific heat, so the specific heat is 4.184 joules over grams times degrees Celsius. Calculate the enthalpy change, and it said in kilojoules per mole. So what we're trying to figure out here is kilojoules per mole. Okay, so what we're going to do is, since here, what I'm going to do is I'm going to do Q SMAT. So I'm going to Q is equal to S times N times delta T. And I kind of look at these as two separate problems. Going back here, whoops, let me show you the bottom of the board. We're trying to figure out kilojoules per mole. That's what X is. Well, I'm going to do two separate problems. I'm going to figure out kilojoules, and then I'm going to figure out moles. So I'm going to figure out kilojoules. I'm going to use the specific heat, the Q SMAT. Okay, so now what I'm doing is I'm plugging and chugging. Now for mass, I had 100 mils and 100 mils, so I have 200 mils total. 200 mils total. And it says that the density is 1. So if I take 200 mils, and I just multiply this, so mils for grams, I would get 200 grams. So the mass of this would be 200 grams. Okay, and then delta T, I'll subtract these two numbers. Whoops, so I have 31.3 minus 24.6. Okay, so if I do the math here, what I get on my calculator when I do that, so I've got 6.7 times 200 times 4.184 gives me this. So I have 5,000, and again, the units, grams go, degrees Celsius go. So when it's in a calorimeter, And again, it doesn't matter what kind of calorimeter. When it's a calorimeter problem, it's going to be SMAT, or it's going to be, I'll show you here in a second, SMAT plus CAT. So if I write this out like that. And technically, my sig figs here is I would want to have 3 sig figs. The numbers that were given were 3 sig figs. So I'm going to make that, and I'm going to put it into kilojoules. So I'm going to go 1, 2, 3. So I'm going to have 5,610. I'm sorry, 5.610 kilojoules. I'm going to get that into kilojoules. Okay, so now I'm going to come down here, and I've got 5.61 kilojoules. Okay, so I've taken care of the kilojoules part. So I just took this number and I put it there. And now the moles part. Okay, so the moles, I'm going to go back here. So I'm going to figure out moles I have of both of these. So now, and so the reaction here, what happened was outers and inners. So we get a NaCO plus H2O. And so the moles I have here, so if I get this into liters, 0.1 liters. So I have 0.1 times 1, so I have 0.1 moles, of the NaOH, and I have the same thing here. So I have 1 liter here. So if I take, 0.1 liters. 0.1 liters times 1 gives me 0.100 moles here. And so that's the number. That is how many moles are reacting. So over here, and the way I'll define this in this chapter is the moles that are produced. And I'll actually define this. The number that's going to go down here on the bottom is going to be the moles of product in the net ionic equation. Whoops, got it. So I went back here. I got the milliliters into liters. So I took the liters times the molarity to give me the moles. I did the same thing for the HCl. And the key thing is how many moles were produced. The net ionic equation here would have been OH plus H plus gives H2O. And if I did this in an ice table, I would have got 0.1, 0.1, and 0. So this would have been gone. And what happens here is these both run out at the same time. What I'm saying here is for moles, so down here on the bottom, where the moles, I'm defining moles, I would define moles going back up here to the moles of product produced in the net ionic equation. Okay, so if I take that 5.61 divided by 0.1, gives me 56.1. Okay, so going back down to the bottom, I'm making you dizzy. So here's my final answer. Okay, it's a good problem, but it's a manageable problem. So we had 2 parts to this. We had the Q-SMAT part of this, and then here on the top we had the net ionic equation ice table, and we put them both together. And again, it's kind of like I do 2 separate problems, and I plugged in for kilojoules from Q-SMAT, and then for moles from the balanced equation. A good problem, definitely a good problem. Okay. So I'm going to do a couple of examples because to me this is really the core of this chapter. And there's definitely, the stoichiometry part of this chapter. And there's also some other parts coming up as well. Okay, so we just did that problem. Okay, and we talked about this slide. Okay, so here is another one. This is going to introduce that the SMAT plus CAT, and I'll explain. So 1.435 grams of naphthalene is burned in a bomb calorimeter. So again, whatever calorimeter, think SMAT or SMAT plus CAT. And you only do CAT like you do in this problem when the heat capacity is given. If the heat capacity isn't given, what they're saying there is that the calorimeter itself is absorbing some of the energy. The temperature of the calorimeter, 200 grams increases the heat capacity. So whenever they give us the heat capacity, we are going to do SMAT plus CAT. So I will show you what I'm talking about. So, okay, so now, again, if they give us heat capacity, So again, I'm going to write out everything it says, just the normal way to do this. So naphthalene, so we have 1.435 grams of naphthalene. It says that it's MW, so this is its molar or molecular weight. So they didn't give us the formula, but they gave us the molecular weight. It's 128.2 grams per mole. I didn't have to look it up on the periodic table. Is burned in a bomb calorimeter. The temperature of the calorimeter in the 2,000 grams of water. So the water, there's 2,000 grams of water within the calorimeter. So the temperature, so the delta T is 25.84. Minus 20.17. And this brings to mind one thing. I'm going to go back. Let me write out everything. It says, and the heat capacity is 1.80. And the units on that are kilojoules per degree Celsius. One thing, as I'm thinking about this, on the previous problem that I did, I made a big mistake. I left out one thing, not a big mistake, but a little mistake. I always do the sign at the very end. So I'm going back to the last problem. So let me go back here. There's one little thing I forgot on this problem. So let me go back here. This problem right here. The one thing I left off on this problem was the sign at the very end. And this, I always do the sign at the end. It's probably a terrible way to do it. But if the temperatures went up, then it's exothermic, and so the sign would be negative. And if the temperature went down, it would be positive. So my answer to this problem, so let me, okay, so the bottom line on that previous problem, the only thing I should have had that I left off was the sign. It should have been negative because the temperature went up. So the sign, so note that. I mean, that was something I left out. So -1 for Mr. Wood, he left out the sign. Always got to remember, I always do the sign at the end. Okay, so note that on the last problem. And then the other thing we're told, so now back to the problem I'm doing on naphthalene. And the specific heat we are told is 4.184 kilojoules per mole. Now what we're trying to find is delta E. Well, remember, delta E is the same thing as delta H. And again, it's in kilojoules per mole. So this time, if this is all the information I'm given, because I've got heat capacity, I'm going to do this. I'm going to do Q SMAT. But if we're given heat capacity, I do SMAT plus CAT. So this is a possibility. It depends. On the previous problem, we weren't given the heat capacity, so we just ignored the heat that was gained by the calorimeter. But in this case, they've given us this. So if I plug in the numbers, so I've got 4.184. So there's the specific heat. The mass is 2,000 grams. Okay, and delta T is 25.84 minus 20.17. So 25.84 minus 20.17 is 5.67. Okay, and then C. Now, and then the CAT part of this. So I come back here to CAT. So the CAT, you got to watch the units here a little bit. So this is kilojoules per degree Celsius. Whoops. And then the T part would be the same number. So it would have been the same number. So again, I check the units. So grams go, degrees Celsius go. Here, degrees Celsius go. So here I have joules and here I have kilojoules. So if I do the math, so I've got 4.184 times 2,000 times 5.67. So what I get here is this, 47,447. We'll come back and do sig figs at the end. And the unit on this again would be joules because grams canceled out, degrees Celsius canceled out. Now here, I've got 1.8 It's 5.67. This would be 10.206, but this would be kilojoules. And they, again, the problem, they wanted us to do this in kilojoules per mole. So I'm going to get this into kilojoules. So I'm going to move the decimal 1, 2, 3. So I'm going to get these units to be the same. So I have 47.447 kilojoules plus 10.06 kilojoules. Gives me 57.6 or 57.7 kilojoules. So that's going to go on top. So I found the kilojoules. Now the moles. Okay, so now for the moles, this time I don't have a balanced equation, but I'm going to use this information right here. So I'm going to go 1.435 grams, and I'm going to convert this to moles. So the molar mass is 128.2 grams for 1 mole. Gives me 0.0112 moles. Okay, so I solve for moles. This time just did a conversion. So then I'll take that and I'll put that right over here. So again, it's like doing 2 separate problems. Okay, and then I'll do 57.7 divided by 0.0112 gives me this 5,151, or we'll say 52 kilojoules per mole. Now this time I don't want to forget the sign, because the temperature increased, the sign should be negative. That's what like I said, I forgot on the last one. And then the final thing always are sig figs, and if I look back at the numbers I'm given, I think I should have 3 sig figs, so I think I have negative 5,150 kilojoules per mole. Okay, so bottom line here is that we're doing now, if we are given the information with the heat capacity, it's SMAT plus CAT. I'm going to do a couple more problems in the next lesson on that. So a good problem. We're definitely in AP Chem doing some good problems. Guys, that is it. I'm going to go ahead and stop this lesson and have a good day.